That one was quite fun, I think. So you can have a peek for yourself. So that's the problem now we are facing. You are doing numerical simulation and you get an answer. How can you get the world to believe that your answer is correct? So to say it crudely, the simulation you have done is worthless without proper verification and validation. So it's very, very important concepts. So this was here. Oh yeah, do you work? Yeah. Something that Maria Fernandino wrote. Then the students were doing Fluent, but still quite okay, I would say. So the problem you face doing CFD, you can very easily get a lot of very, very fancy images, very fancy pictures, animations, whatever, and it looks very, very impressive. So you might bluff a lot of people that, oh, this must be very, very good. And it can be just rubbish. You can't really tell necessarily from these complex problems how well are your results, how accurate is it? Does it have anything to do at all with reality? So you have to somehow validate and verify it. You have to convince your listeners, your readers, that it is correct. So, of course, you can take your data and then start calculating different quantities, but you need something to compare with. And that is, or can be, very, very hard. If you are simulating something that nobody else has done before, then what do? You have nothing to compare with. So, how can we sort of trust these different solutions? We will have the standard errors, of course. You have numerical problems. You have a discrete version of the original partial differential equation. It's only second order, third order, fourth order accurate. You have been programming something wrong. That's not so fun. And you are sitting there as an amateur using the software wrong. Insert negative viscosities and stuff like that. Then, of course, you get an error. And also, you have a lot of questions with the real-world problem you are trying to simulate. What boundary conditions can I use to express or to mimic the real world correctly? What models do I have to use? What are the different demands for using these different results? And so on and so forth. So you have a lot of questions, a lot of problems. These errors, of course, we have sort of, or should have, control over them. The round-off and discretization errors, stuff like that, they can be reduced, they can be controlled, we can put a number on them. The coding, of course, must be tested so that you know that the program is correct, and you have to learn how to use the software. So that shouldn't be a problem. So, as you now have learned, you need sometimes better resolution. We had the discussion, for instance, for stability reasons, the cell Reynolds number had to be smaller than 2, if you can recall that one. You have maybe some local areas inside your computational domain with very strong gradients. Then definitely you need to resolve that area quite nice. You need more cells there and so on. Careful using unstructured mesh systems. There you might get some additional false diffusion just from your mesh. And so on along the line. You have many things here to consider before you can start believing in your own results. And also remember, if you are choosing this and this model, of course your results can't be better than what this model is designed to do. Of course. So very easy here to get bad results. And sadly, these commercial codes, CFX, Star CCM, Fluent, expensive software, they are very robust. So they will sort of try to obtain a correct solution, not correct solution, they will pretend at least that they have a solution, even if you have done something very stupid with input values. So you sort of have to validate and verify the results somehow. So how to do it? First, verification. You have to solve the equations, and you have to solve them correct. So that one is not so hard to fight. You have sort of a numerical problem there, finding the solution within some accuracy. So finding a solution for a set of algebraic equations, that's something that we can do. Finding the residuals, check that you have enough iterations, and so on. So that one, finding, solving the equations right, that's something we should be able to handle quite okay. And yes, you can get a result, and you should then be able to print the result equal something plus minus some percentage. So that should be a possibility. And of course, the code must be correct if you have written it yourself. If somebody else has written it, then you have somebody you can crucify if it's wrong. Check the convergence, residual values, and so on. And performing a consistency check. Yes, that is something tending more towards physics, like mass conservation. I mean, you have a computational domain, whatever problem you might have, sending something in, sending something out. Then you have your physical equations, say the integral formulation. How do they look? Well, you will have here the derivative of the mass inside a control volume plus the fluxes through the control surface of rho, and then velocity dot normal vector dA has to be equal to 0. This equation is unquestionable, regardless of the choice of control volume. So as a control, yes, you can take the entire domain. You can take any domain. And of course, this equation should be fulfilled. Of course, we use this equation for one single cell when we do a finite volume method, or finite element for that matter. But you could use this equation afterwards to test your results for any domain, no matter what. Of course, it should be fulfilled. And then you can continue checking this one, the Newton's second law of motion, control volume analysis, or rho, and now velocity vector, change of momentum inside a volume, and then for the fluxes through the control surface, like this. Of course, this equation should be fulfilled for any volume, unquestionable. And if it's not, then you have done something wrong. And you can test it for your entire domain, or just pick a part of your domain and just see that, yes, these equations are fulfilled. Just as controls, you can't really say that, okay, he is decently fulfilled for this domain. Then you can't conclude that, okay, then I have a correct solution at every single small little volume inside here. You can't really say that, but at least you have checked something. Typically what you would do here is, say you have a flow around a blunt object or something, then you will find the drag force acting on this blunt object. So you have flow around the cylinder, for instance. How to find the drag force? Well, you look at the pressure forces acting here and on the other side, net pressure force, and then you will have the shear stress acting on the surface, and then you integrate all the forces locally around this blunt object, and then you find a drag force and maybe a lift force as well. As a control, you put a control volume outside here. And then you look at fluxes in and out of this control surface, and you should get the same answer. So that's a very good test that you have completed your equations correctly. Some grid dependencies. Now that is also a pain. It would be very nice if you could obtain what's called a grid-independent solution. So you do one simulation, you get a result. Then you refine your mesh, twice as many cells in all directions, and do another simulation. And then you get different results. And so you continue until you see that the results tends towards a constant value. Then you have a grid-independent solution. That will never happen. You don't have time and you can't afford it. So at least you should try with several grids and then see that at least the tendency should be towards something. This will be a real pain when you are using turbulence models. We should say something about that as well. Because several of these turbulence models, they require that your first grid point is outside the viscous sublayer. So many of these turbulence models, they will be high Reynolds number models. They are built for calculating problems where the plus units here, they are so small that you hardly see it inside your domain. And then they will require that your first cell point, your first velocity close to a wall, should be, say, around 100 or something, at least bigger than 10. And then if you try to refine the mesh, do the same simulation with finer and finer mesh, then you jump from this side to something down here, you get a completely different answer, and you get a totally wrong answer. So there, trying to achieve grid independency, you are in for a big surprise. Then you have to switch turbulence models. If you are able to resolve this region, then you need a low Reynolds number model. If you are outside here, then you need a high Reynolds number turbulence model. So obtaining a grid independent solution, wow, that's a real pain. And in practice, I would say forget it. But if you have time, if you have the possibility, you can do a couple of simulations at least and see that the tendency looks sensible. Yeah, temporal convergence depends on your problem. Is it a time-dependent problem, or is it only a steady state that you are interested in? Then validation. Now we are talking models. The first one was solving the equations right. Now it's a question, are we solving the right equations? So now we are talking about comparing your end results with the real world situation. So this, of course, will be dependent on the input and also the different models you have chosen to use. So here, to get a validation, you definitely need a correct answer, sort of a facet somewhere, experiments, somebody has done some similar things before, you have something to compare with. Or else you are a dead duck and your work will be worthless. You have to have something to compare with. So if you have some data from some experiments, then hopefully your simulation should be inside the range to validate it. If it's outside, okay, then you have something wrong. What would be nice, of course, when you have some data to compare with, if they have specified some arrow bars, if they have some plus minus values on them. That's not always the case, so it can be hard. But you need to find something to compare with. So some experiments or some other heavy simulations, some DNS, very nice to compare with DNS data. So this is what we would have liked, to have experimental data, the black lines, with plus and minus range, and see then are we within or outside the range, the validation range here. But that's not always the case. So search for good data. And if you don't have any data, then what do you do? Well, you have to do something. So see if you can find some DNS, LAS, whatever. You can of course do these consistency checks. That's also one way to say, maybe not totally validate your simulation, but at least improve the confidence in your results that these equations are fulfilled for, say, a couple of different arbitrary domains. Say now that you are going to do a simulation of something very, very complex. Nobody has looked upon it before. You don't have any experiments. You can't afford to do any experiments yourself. Nobody has done any simulations like this before. You are really, really on thin ice. What do you do? Then I would suggest you take your problem, say the original problem, very, very hard, complex, airflow around a complete oil platform or something, I don't know, whatever, and surface waves down here as well, something like that. Very, very complex problem. You are going to simulate this, and you have nothing to compare with. It's not built yet, and what do you do? Well, break it up. Take one single part, the flow around one of these objects, and do a study of that alone, and see how the flow behaves, and then seek data for just this one single building. Then you should achieve some results here, gaining information, how fine mesh do you have to use to get a decent result just for this part of the real problem. And when you have a decent result here, then you can sort of expand your problem to cover everything. And it would then be reasonable to assume if you can handle part of the problem, then it should be fair to say that now I can handle the entire problem as well. So break it up into small pieces, small test pieces. That's one way to obtain a validation if you don't have anything. Some links here where you can find some sets of data. The CFD Online, that is quite an okay place to start if you are a little bit on thin ice. You can post questions there and people actually will answer, so it's quite active. So CFD Online, that's a good place to start. So you have the links here. And of course, a whole bunch of journals, many libraries full with different journals. So that's possible. When you do a report, then you should actually give enough information in your report that next year a reader should be able to copy or duplicate your simulation and get the same answer. So you should provide him with enough information that he should be able to repeat what you have done. So that's something that you should have in the back of your head when you do a report on a job. Of course, it will be a lot of input files, not necessarily something that belongs in a journal article or in a report for that matter, but then at least in an appendix or something. Yeah, I won't go through all this. Recommendation for grid here, that was for the fluent users, that this one has been written. So I won't go through all this. Yeah. The other you have been given was just a chapter I stole from a numerical book. It's quite okay, actually. A little bit more in depth of verification and validation, but actually roughly the same. So you can have a peek into it if you want. So verification, that you have solved the equations right. Have to fight with that one first to get a solution, and then you can start looking into your solution if it has something to do with the real world. Talking about validation. So it can involve many simulations, trial and error, if you want to do one single job, one single simulation actually. Yeah, I won't go through this one, you can read for yourself, but it's fairly decent written, and here also you have a little discussion here about this grid independency concept, and talking about extrapolation. As you all should be aware, extrapolation is something very bad, you should never do it. Interpolate, okay. Extrapolate, no, then you go outside. But it's sort of a way to use several simulations, finer and finer mesh, and then sort of extrapolate to the correct answer and see that this extrapolation doesn't blow up. But as I said, with turbulence models, then you are in a problem there, in a bad fix. When you are sort of resolving the ball better and better, then you better use the correct turbulence models, or else you're in trouble. Yeah, I won't go through any more of this, but remember, verify and validate, or else your work is worthless. Next week, it will be open foam. So if you want to take part of it, you are free to come. Bring your laptop. If you don't have Linux and open foam installed already, then be sure that your laptop can boot on a USB memory stick. So you will be given a USB pin with an Ubuntu and with the software OpenFOAM already installed. If you have a Macintosh, then you're in trouble. I don't have any Mac operative systems there, so that doesn't work. I have some old laptops you can borrow if necessary. And if you find another Intel machine, then it can be an old one. It doesn't really matter. We are just going to do very small test cases anyway. So bring a PC, and then we will have fun with OpenFOAM. Any questions from you?
Can also introduce some method you use for verification? For example, mesh like grade convergence. How do you approach. For example, I think I used like Richard's interpolation and see what auto accuracy we have, something like that. So like, how take a grid convergence example. How do you do that mostly? You just plot them and compare, or there is some mathematical method?
You find a little bit description of it in this chapter here, actually. So I haven't gone through it in detail myself, but that's at least a good place to start. I think you have different way of doing this if you want to have it shown graphically. But then you should take your program, the code you're using, and then run sort of a test case where you say you have an analytical solution, and then compare it. Then you know what the exact solution should be. And according to Lux, we said that, okay, the smaller and smaller the deltas becomes, the closer you should get to the correct physical or analytical solution. And then you can see, is this really the case? So of course you do a test case where you have an analytical solution. Yeah, that's a decent place to start. Other questions? Then we stop here.